Welcome to the Peacademia course on the basics of semiconductors. This lecture covers the direct and indirect semiconductors. Let's start. By the time you finish this lesson, you will learn the charge carrier's momentum and energy, KSpace energy diagram, and direct and indirect semiconductors. In the previous lectures, I introduced the energy band diagram and the diagram plotted versus the interatomic distance. In this lecture, I want to introduce another energy diagram that is plotted against momentum and is called the KSpace energy diagram. As we will see later in this lecture, using the KSpace energy diagram, we are able to categorize semiconductors into direct and indirect. Imagine you're given a single resting electron in a vacuum. Without any electric fields, the electron velocity is 0 and does not move. If I add two electrodes, one on this side and another on the other side, and I create an electrical potential difference between the two electrodes using a DC voltage source, in this case a battery, an electric field is generated between the two electrodes. The direction of the electric field vectors is from the positive electrode to the negative. This electric field exerts force to the electron, and as a result of this force, the electron gains some kinetic energy moving towards the positive electrode. The force F equals minus Q, which is the charge of an electron, times the electric field. Q equals 1.6 times 10 to the power of minus 19 Coulomb. The electron kinetic energy E equals half times the electron rest mass times velocity squared. The electron rest mass is a constant and equals 9.11 times 10 to the power of minus 31 kilogram. Since momentum equals mass times velocity, the kinetic energy of the electron under the discussion can be rewritten as momentum squared divided by 2 times the mass. If I plot the energy versus momentum using this equation, what we can see is an upward parabola. Electrons can behave as a particle and wave. So far, I discussed the electron momentum when it behaves as a particle. What if the electron behaves as a wave? As a wave, an electron has a wave number shown by k. K equals 2 pi divided by the electron wavelength or lambda. The momentum of a wave equals h bar times k. H bar equals h over 2 pi. H is the Planck's constant and equals 6.62 times 10 to the power of minus 34 meter squared kilogram per second. If you remember my talk at the very beginning of this lecture, I talked about the KSpace energy diagram. After defining the wave momentum and wave number, it should be clear now that the energy can be plotted versus the wave momentum or wave number. That is why we call this diagram the KSpace energy diagram. The motion of an electron in a vacuum was a very simple example to explain the energy momentum diagram or the KSpace energy diagram. But what happens to the motion of a charge carrier, an electron or a hole in a solid state semiconductor? Let's say in this two-dimensional lattice, I have two charge carriers, an electron and a hole. Because of the existence of other atoms in this structure, the study of a charge carrier momentum looks a complex task. However, this complexity can be significantly alleviated by using the effective mass of the charge carriers. This enables us to use the same energy momentum equation we developed for the electron in a vacuum. For silicon, the effective mass of a free electron is 1.18 times the rest mass, and the effective mass of a hole is 0.81 times the rest mass. For gallium arsenic, the effective masses of electrons and holes are sitting right here. These two equations describe the energy momentum for the conduction and valence bands of a particular semiconductor. Let's draw them and see how they look like. In this diagram, EC and EV represent the absolute minimum and maximum of the conduction and valence bands respectively. Those semiconductors having a phase-to-phase maximum and minimum of valence and conduction bands are called direct semiconductors. There is another type of semiconductors called indirect. These equations represent the valence and conduction bands of an indirect semiconductor. In indirect semiconductors, the absolute maximum of the valence band does not have the same momentum as that of the absolute minimum of the conduction band. It is worth it to mention that the absolute maximum of the valence band is always at the zero momentum. Here you can look at the KSpace energy diagram of silicon. As you can see, silicon is an indirect semiconductor because the absolute minimum of the conduction band is far away from the absolute maximum of the valence band on the momentum axis. Here is the KSpace energy diagram of the 4H silicon carbide. This semiconductor is also an indirect one. Here are the KSpace energy diagrams for gallium arsenic and gallium nitride semiconductors. Since the absolute minimum and maximum of conduction and valence bands are at the zero momentum, they are direct semiconductors. In all these KSpace energy diagrams, you can see that most of the states are accumulated around the maximum and minimum of the valence and conduction bands. You may now wonder why we care about a semiconductor to be direct or indirect. This is a really good question. In indirect semiconductors, the recombination yields primarily photons, and in indirect semiconductors, the recombination yields lattice vibration, called phonon. The lattice vibration generates heat. Direct semiconductors are often used to build lasers, LEDs, and optical semiconductor devices. In this lecture, I talked about the charge carrier's momentum and energy, KSpace energy diagram, and direct and indirect semiconductors. In the next lecture, I will discuss intrinsic semiconductors. Thanks for joining this lecture of Peacademia.